Okay, we've got not relative rates of growth, sorry. We've got fourth and seventh terms of a geometric sequence here. We're told that the fourth term is 54.7 and the seventh term is 54,700. So it looks to me like some sort of power of 10. And they want us to find the first term, a common ratio, and an explicit rule. Okay, so three kind of big things here. What I'm going to do is I'm going to work with the first term here in a minute, but I'm going to just rewrite these guys and not call it fourth and seventh. I'm going to call it for my problem the first, okay, and then 5, 6, 7. Okay, so first, second, third, fourth term, okay, of the geometric sequence. So what I'm going to do is I'm going to treat this as two parts. I need to figure out what my common ratio is. So what I'm going to do is I'm going to say that A1 is equal to 54.7. Now, this is not the A1 we're interested in, but in order to find what I'm looking for, I'm going to start with what I have to begin with, okay? And I know that my fourth term then is equal to 54,700. So I know that in this case n equals 4. I know that in this case n equals 1, okay? And so what I'm going to do is I'm going to say A4, 54,700, is equal to my first term, 54.7, times some number to the, and remember how we just did on the previous geometric sequence where we were 1 before? So I'm going to have the 4 minus 1 power, or x cubed. I'm going to actually work with this problem right here. The reason that I look at it this way is because, remember, when we're trying to find that very first term, we need an n minus 1 minus 1 is 0. Anything to the 0 power is 1. So keeping that kind of pattern in mind, I'm going to work from this point right here. I'm going to do my math real quick. Divide that 54.7 both sides. So 54,700 divided by 54.7. And I get 1,000. And that's equal to x cubed. And take the cube root of everything here. That's going to be 10. Okay, so this x then is going to be my r value, my common ratio. So going back to the question that we were asked, my common ratio is going to be 10. Okay, and we want to find the very first term. So we're going to borrow what we did right here, but now we're actually going to find the first term that we started with. So to do that, we're going to say that the fourth term, okay, the fourth term is equal to 54.7, the actual fourth term that we are told for our particular sequence. So 54.7 is equal to the first term times the common ratio to the n minus 1 power. Okay? So this is what it's going to look like. And we're trying to figure out where we started. So go ahead and do 10 to the third. That's going to be 54.7, which is equal to 1,000 times the first term. Divide both sides by 1,000. And you get 0.0547 is equal to a 1. And ask yourself, does that make sense? What happens if I multiply by 10? You move the decimal over. What happens if I multiply by 10 again? You move the decimal over. And we should see that we will get a fourth term of 54.7 doing this. Okay, so we kind of have to work this problem twice, and we're taking almost the same identical steps both times. Now, they want an explicit rule for this, and we really needed the first term to be able to do that. Because what we're going to do is take that first term times our common ratio to the n minus 1 power. So once we know what our first term is, we know what our explicit rule will be. It will be 0.0547 times 10 to the n minus 1 power. And that's really all there is to it. So you have to work this one through twice once using the fourth and seventh terms as our first and fourth terms, and then again using the actual first and fourth terms. It looks a little confusing, but if you'll work this problem through on your own and actually write it out so you can see what happens every time you multiply by 10, you can see a pattern develop that allows us to solve the problem the way I did right here. Okay, now we want to find a limit of a sequence, if it converges, if it doesn't, if it diverges. So now with question 5, we're trying to investigate what's going on with this guy for really large values of n. Remember, when you're looking for whether there's a limit to a sequence or not, we want to know when n is 5 million, what's our sequence getting close to? Is it continuing to grow? Is it shrinking? Is it approaching a flat line? So the thing here is to just imagine what you would do if you were looking for a horizontal asymptote. And in that case, we would look at the leading coefficients and the leading degrees of the numerator and the denominator, okay? And that is going to give us our biggest clue, because for large values of n, then we really don't care about adding 2 or 5. We really care about what the degree reduces to, or what the leading coefficients reduce to. In this case, the degree on the bottom is larger than the degree on the top. So if I just look at these first terms and I set up a fraction, n over n squared, because if you really think about it, 10 trillion plus 2 and 10 trillion plus 5, there's not a large difference there, okay? Or 10 trillion plus 2 divided by 10 trillion squared plus 5. The 2 and the 5 make no difference at all when you're dealing with large values. They're not significant. So what we want to do is we're going to look at the common, we're going to look at the ratio of the leading terms from the numerator and denominator. And if these approach a specific number, we're going to then look at the -1 situation. If they don't approach a specific number, if they approach something like 0, then we'll be done. Well, in this case, when I reduce, I end up with a fraction that looks like 1 over n, okay? And when I plug large values in for n, and you can do this on your calculator, 1 divided by 100, 1 divided by 1,000, 1 divided by 100,000, 1 divided by 1,000,000, 1 divided by 100 million, 1 divided by 1,000,000,000. If you will just take the time and punch that into your calculator, what decimal value are you approaching? You'll never get there. But what are you approaching? What is your limit? And in this case, our limit will be 0. Okay? Since we have a limit, a constant limit right here, 0, this is our constant, we would say that this limit converges. Okay? So the limit as n approaches infinity of -1 to the n power times n plus 2 over n squared plus 5 equals 0, and because it equals 0, it converges. Now, think about this. If we looked at this same problem and we made one change, the limit as n approaches infinity of -1 to the n power of n plus 2 divided by n plus 5, what would we say about this one? Does it converge or diverge? Okay, does it approach a specific number? Does it approach 0? Does it approach anything at all? Well, again, if you'll just look at the leading coefficients, look at the leading terms, what's going on with these two guys? What does it reduce to? Okay, and if we take these leading terms and we reduce them, we're going to see that we're going to get a 1. So n divided by n is 1. All right, so the fraction part of this guy, as n grows really large, approaches 1. Now, look at the -1 to the n power. What happens is we're going to have -1 times 1. We're going to have -1 squared times 1. We're going to have -1 cubed times 1. And what you're going to see is we're going to bounce back and forth between -1 and 1. So in this situation down here, this one would diverge. It just does not approach a specific number. Yes, it approaches a 1, but because you multiply by a -1, it bounces back and forth and back and forth and back and forth. It never approaches a specific number. Now, on the problem that we were given, it also bounces back and forth. But each time it bounces, it gets closer and closer and closer and closer and closer to 0. And that's why we can say that the one in red converges and the one in teal diverges. Okay, on this problem, we want to look at whether the limit as we go to infinity of this particular sequence converges or diverges. And the interesting thing that we need to keep an eye out here is the n. That tells us what's going on and where it's happening. And so we want to know what's happening when n is not just 0 or 1 or 2, but we want to know when n is 5 million or 6 million or 7 trillion, what's happening to this guy. Well, let's just investigate real quick what the sine looks like, the graph of the sine curve. Now, the pi over 2 is going to change our curve just a little bit by making it a little wider or a little narrower. So in generalities, though, what we have for the sine curve is a situation where we go like this. And so when I change n, all that does is increase the width or decrease the width of each wave, okay? And you can graph the sine of x times pi over 2 and see what it looks like. But notice that as we graph this guy, we bounce back and forth between +1 on the top and -1 on the bottom. So it just depends on where we're at on the x-axis, which would determine what's going on at that particular place. And so when I graph this guy, the pi over 2 makes a slight change in the width of my graph, but the graph never goes above 1 or -1, and it depends on where we're at for n. So when we investigate the limit as n goes to infinity of the sine of n pi over 2, then what we're going to find is that this guy diverges. It's just going to bounce back and forth between -1 and 1. It never goes above 1. It never goes less than 1. Because when you look at the sine of any number, when you look at just the sine of any number, the largest value that the sine of anything could be would be 1. The smallest value that the sine of anything could be would be -1. And since we never get out of that range, we can't have a specific place that the sine converges to. So this limit diverges.